Oh my. Samuel, yes, I think I can hear you. I heard you just now. I think we can now safely go ahead and start the event.
Hello, am I audible?
Yes.
Okay, hi, I'm Kevin speaking. Uh, I think there was a little bit of technical difficulty going on. I think something's wrong with the audio or something. So I'll start with a little bit of introduction. Starting with we are TensorFlow user group Mysore. We conduct events like these to promote open source technologies and Google technologies so that people are more aware about it. And if any one of you out there are interested in conducting a session on a technical event, something like this, like we are doing in this session, then you can contact Ms. Usha Rengaraju. Ms. Usha Rengaraju is a data scientist and she has played an active role in making these events happen. And she is the first female Kaggle Grandmaster in India. And do follow her on Twitter. And if you have any queries, you can contact her there. Links are in the description too. Uh, and coming to the core team now, the next slide. The core team consists of these members, as you see, and we are the common team for three different organizations. We have TensorFlow User Group Mysore, there is GDG Mysore, and Women in Machine Learning and Data Science Mysore. And it's because of the collaborative effort of all these members that we have been conducting events successfully. And if you want to stay tuned with the further events, we conduct events like these every week, and from all these three organizations. So if you want to stay updated, you could check out these meetup links which are shown here. And we have three community partners. There is Co-Learning Lounge, which is a collaborative learning platform where you have a couple of data science resources. Do check them out. You could download it. And then we have Applied Singularity. Applied Singularity is, again, they too have data science resources, and they also have an app. Then we have Confub. Confub is an online platform where you could host events like conferences, and they have well-known clients like Red Hat and Microsoft. So do check out these partners, and I put up the links in the description. Do check them out later. So without further ado, we'll get started with the session. So you could start now. Sorry for the delay.
Part and parcel of all such kind of events is
Yeah.
application of which laws, if I may ask? Murphy's laws, right? So that I take it in stride, and I call any event successful only when such kind of delays happen. So with that, let's get started. Uh, so guys, I'm Gunjan. I work with Fidelity Investments as a principal data science, and what we are going to talk about today and in many more sessions to come are the topics which are close to my heart, not as much close to the actual things that I work on day-to-day basis. So I am a learner just like you, many of you are. And if you guys are experts at some of these things, I would be the, sort of the person on the lower pedestal looking up to you guys for learning from you, right? So with that kind of a platform, let's start discussing certain things as we go along, right? First of all, let's just say hi to each other so that we understand that I'm reaching out to you properly. All my audience, can you hear me fine? Can you see the screen nicely? There is no Murphy's laws at work here. Can you just quickly say something so that I can take that as my assurance and move on? I'm sure there is some delay. Let's just see if the audience is responsive or they have gone to sleep already. All right. So let's get started with the session, shall we? When we talk about AI on edge, right? What exactly, uh, do we think about the data basically? So if you remember, when I was working on SQL and then Hadoop as a data transformation layer came along, I had to think through and I had to realign myself with that way of distributed data, thinking about distributed data, right? So those are what are called trends in data space, correct? So what is the current trend, latest trends in the data space? Any comments around that? What do you feel like in your own reading of stuff, right? In your own understanding of how the world is working right now, especially in the day and age that we are living in. And I hope everybody uh, who are here along with their families are doing well, keeping safe and keeping healthy, right? But what are the trends in the data that you observe given all the backdrop, or rather especially the backdrop that we have today, when we speak about all such things? One thing which comes and jumps at me is the fact that data is actually born at the edge and it thrives at the edge. Now what does that even mean, right? What is the meaning of edge here? Edge means the place where interactions happen. That's how I define it. Now you don't go and try and find out that definition and prove that definition anywhere else in dictionary thesaurus or any such other source. What I'm trying to point out is the way I understand my world is edge is any place where there is an interaction, uh, there is some sensing that is happening, there is some interaction that is happening which is being captured, right? And one of the most important edge devices for that matter is what? Can you guess? So we have trends in data wise, we have horizontal and vertical scaling, multitask learning, streaming data, localized data. There are so many suggestions that our friends have sort of uh, uh, pinged here in the chat, right? So the question that I am now asking is, yes, one of the most important things that interactions, where interactions happen, are mobiles, correct? So that's one, like that's where I thought I would sort of start this whole discussion, isn't it? So the reason why we should be aware of what is happening in the space that we are living in is because everything that is happening for audience at this particular level. And if that is the outlook, we should be very very prepared to see how exactly the trends are with regards to machine learning in this space, correct? If data is going to be residing in such kind of small devices, right? How exactly are we talking about working with machine learning algorithms on these devices? Because if you have heard about, say, OpenAI's GPT-3, how many parameters have you heard it has, GPT-3? Just a quick quiz. I love quizzes, by the way. If you have heard me taking my discussion somewhere else, you would see me taking quizzes as part of the discussion, basically to set the context. Okay. So how many parameters are there in GPT-3, by the way? A billion or a lot more than that? What do you feel? There are more than 175 billion parameters. Now imagine such kind of model. If you want that model to run on this device, will it be able to run? The simple answer is no, because these devices are restrictive in terms of the resources. And what kind of resources specifically? Computational resources, right? However, there are things which have been happening over the years, and you and I are, feeling that change happening on day-to-day basis, right? My last phone some 3 years back was far inferior than the phone that I have today. Correct. So basically, even the edge devices are improving in terms of their latency. They are capable of working offline. They have a better battery life, and the most crucial advantage that they provide to you as a product owner. So look at, like, every problem needs to be thought through from various angles, right? One angle is, well, that of a data scientist. So okay, I want to create a huge model which is doing great job at 10 different things, like GPT-3 for that matter, right? I created, but then comes the product angle to it, right? How will I utilize that model? Can I push that model onto the edge device? And if the answer is no, a lot of use cases are then negated just because of that answer. Correct. So from a product space, or from a product perspective, or from a consumer perspective as well, what if I don't want to send my information out, right? Such kind of edge devices hold the key to provide the privacy advantages which today's governments are enforcing on the companies, as well as a active consumer such as I would never like to part away with my data, right? So what does this all mean? On one side, resource constraints, on other side, data issues, trends in data. What does it all mean for analytics and personalization? Right? Because why are we doing all of this, right? At the end of the day, it is for personalization, right? All the applications that are there on that small little phone of mine should be doing exactly what I want them to do, right? Should be tuned exactly to my own personal taste. That's what we are doing using machine learning by and large. Wouldn't you agree? So this discussion is going to be a very light discussion, and it would help if you keep commenting, if you keep asking questions, and make it conversational as much as possible, right? So I promise you, this is just the first of the very many talks that I have planned for you guys. And so therefore I will keep it very light. Almost, I think, unless we are doing well on time, we will not delve deep into any code and stuff like that, right? So that's the charter. So keep the conversation going. That's my personal request to all of you, right? So coming back to what we see on the screen, what does it mean for analytics and personalization, right? So this is just one aspect of it, trends in the data, right? Look at it now. What is the fundamental question we asked? What are the trends or future for analytics and personalization? One option can be, don't use, because privacy is a real and valid concern of consumers, of governments, everybody alike for that matter. One option is, do not use data and do not improve the products. Do you think it is a valid option? It is actually something that you, as a company which thrives on the information that you get from the user, would like to go with? Never, right? Each and every company would like to improve upon their offerings, improve upon their products by utilizing the way in which they are being used by the users, and by understanding the usage patterns of individual users, and then keep improving their offerings and keep fine-tuning their understanding of the consumer. Correct? So this is not an option anymore. Of course you would want that data, right? So, well, then take permission and use the take the data centrally. You consume all that data. You many of you mentioned clickstream data and streaming data and stuff like that, right? What is this? It is exactly that, right? It's that take the permission, bring all that data in a central place, and you know use whatever Google Cloud Engine or Google Compute Engine or whatever you want, and run tons and tons of algorithms. And well, if you want to do that, by the way, you just have to wait till our Ram comes in and tells you how to do it most efficiently. Yeah. So that is something I will just leave as footnote and move on from there. However, if you want to do that, you will have to bring all that data and keep it centrally, right? Now that is where I raise the concern basically about privacy. It is not I alone. As I said, CCPA, California uh, Protection Amendment. I really don't know the full form, and I am really sorry for that. But GDPR, CCPA, there are laws being passed across the world to govern and sort of safeguard individual safety and privacy from the organizations, right? So beyond a point, it becomes a legal requirement many a times to not allow this from happening, right? Or to avoid this from happening, right? So then what to do basically? What is the solution, right? That's where we are right now. Are you with me? That's where we are right now. So now the question therefore is, let's look at the question therefore is still out in the open. Like what happens if privacy is such big a concern? What happens to the analytics and personalization per se, right? So that I will just for a bit, I will leave it hanging. And let's talk about a different angle here, different viewpoint, right? The first viewpoint we saw was that of data, right? Let's talk about a different viewpoint, which is trends in infrastructure, right? So I'm sure all of you would know how machine learning works, right? There is data, right? There is a server. You have your machine learning algorithm there. You take the data, load it in the RAM, learn that so-called complex, very nice and shiny machine learning model, and that's done, right? It is as simple as that. But the problem is, when you have huge amount of data, then what do? This works when all your data, right? Keep commenting, guys, keep commenting, right? Whatever you hear from me, if you have any thoughts around it, please keep commenting. I'm continuously checking for your comments, by the way. Yeah. So I get back to this and I ask you again, in a simple setup where all your data can be loaded to the RAM, and therefore, or otherwise there are other ways to sort of keep batches in the RAM and then keep learning from it, you can learn a model using the data that you have and be ready with it, right? What if this is no longer an option? What if you have such a humongous data that you need multiple, or no one machine is going to be enough for you? Then what do? That is the question for you, right? What would you do? How would you sort of think solving about this problem? Let us remind ourselves, is this problem any different than the problem that we had when we were working only with simple SIMD kind of SQL databases? No. Then what is the, take the hint, and what is the answer? Of course, we want to distribute the workload, isn't it? So you have your data saved here, central repository, all that fine. The issues, privacy issues are not going anywhere, right? However, at least you have sort of solved for the basic problem that, you know what, you have a data saved at the central repository, you spin up multiple servers, each server takes a sample of this data. Are you hearing me? Each server takes a sample of this data, learns a model, and then sends that model to a central server, which will sort of aggregate the results, create one single model of all the models, and then that quote unquote meta model will be pushed across to all the servers, which will then take that as its starting point and start the process again. Are you with me? So step one, we will break the data such that you see this is very, very important here, right? The probability distribution of the data, of the features, so to speak, right, should be approximately same across all these servers, so that you can reliably sort of aggregate the resulting small models which are coming from individual servers like this to this main server, right? So this is your main server. These are your so-called slave servers, maybe, but not in the master slave kind of a way, but still, I mean, in a generic way, right? So all these servers are training one model each, and that model is being trained by a consistent slice of data which is very similar to each other from the overall data, right? Then they send this their individual models to this main server, which then consolidates all these models to one single model, sends that model across all these servers, and the cycle continues, right? Superb. So now you have sort of solved the distributed training perspective of this. Are you with me? Is there any question here? This is important, right? This is not a bad idea. Definitely not a bad idea. But, as our friend from Google here will tell you, that it is not a great idea as well. Ram will argue with me immediately and say that, boss, if all these servers are kept in one single floor of a data center, then this works. Are you with me? Are you hearing me? So what is the practical problem here? For Google scale, for Facebook scale, for all these Amazon, AWS scale, right, where the data is so freaking large that it requires servers across even data centers, forget one single floor of data center or whatnot, right? This provisioning of server is not a problem. This training across servers is again not a problem, but this transfer of this information across the warehouses to a central server, then that server sort of summarizes the models, and then it sort of spreads that model across all these data centers again. That is the information bottleneck in this whole process. The information bottleneck, I repeat, is not in computation, it is in transfer of the information, right? So while we were trying to solve one particular problem of sort of training at scale, we ended up getting into another problem where it was more about transfer of information or communication of information than training itself, right? So these are some hairy issues, engineering issues, when we talk about a huge scale of a problem, right? So that is another angle which is at play here. So first one is privacy, right? Clearly that is coming from a legal standpoint, from a customer experience standpoint, and XYZ, right? There are various teething issues there, right? Second angle is, even here, infrastructurally it makes less and less sense to sort of aggregate data at one single place and then create models to solve a particular problem, right? So then what is all this telling us? That's where now we are at the precipice of everything, right? What is all this telling us? This is the way to go. What you do is, you keep the data in such a way that wherever it is generated, you train your model there, right? You train your model here, you train your model here, you train your model here. You bring that model together, but yeah, I mean, at its own leisurely pace, and go across this particular thing without any compulsion, right? What I mean by that is, even if in a particular cycle this particular server fails, it is fine. Check that, leave that aside, and just go ahead with the training, right? If such kind of framework is available, A, and works, B, then it's a very interesting world, because now we are not, let us just, for I'm putting everything side by side just for comparison's sake, right? So here we are not complaining about scale of data. We are not complaining about data transfer related constraints, and we are also not complaining about the distribution being consistent across all these servers. The only question is, does this exist? I mean, is it even possible to have something like this, something as free as this, and it should work in real use cases, basically, right? That's where federated learning comes in. You are seeing this secured or secure aggregation as well, and that is sort of privacy preservation by and of itself is a very nuanced and very interesting topic, which is possibly what I will speak next time around whenever I get chance. But for now, let's focus on the fundamental of federated learning itself. Okay, so this is how it looks like. Let me just check if there are any questions. Yeah. Uh, okay. Yeah. Okay. So this is the view of the world that we are going to live in. Okay. The engineer such as I, right, would create an initial model. Okay. Now, how will he or she create an initial model? They will use whatever information is available at their disposal, either because of open source data sets or whichever way, right? The historical data set which is available within the company and XYZ, right? Let's assume some starting point exists, right? They create that first cut of model, push it across. Now what happens? That model is pushed across apps across the users. Say you have some 100 million user base, let's say, right? Or 10 million user base, whatever it is, right? What you do then is let the training happen on individuals data. So my mobile, right, I let that model run on this particular mobile, and on the data that I have generated myself, right? No other data is now available. The only data that is available is that is generated by me, right, as an individual, right? And then a new model is created. So you see this trapezoid. I think that's what from class 10th. I remember this particular shape. This is the new model which is generated because of my data and learning on my own mobile or my own edge device. Are you with me? Now, because you have so many users, correct? What will you have? You will have a lot many such kind of models. What do you do? How do you think you can create such kind of an aggregated model out of all these models? What do you feel? Any guesses? So you had an initial model, you push that model across all the users that you had of your app. Now those users have started consuming the model one way or the other. They have generated their own individual data. So this user does not know what this user has done, this and vice versa, right? So now, because that is the case, the training is very, very local in nature, right? So this particular new model is very specific to likes and dislikes and usage pattern of this user. Similarly, this model is, very specific to the likes and dislikes and user patterns of this user. Now we are calling in all these trained model, individually trained models, and we are asking a question. Let me think. I have so many, a million odd models now. How can I generate one single model after sort of combining all these models together, right? And I have gotten an interesting term coined at me, which is called federated averaging. Absolutely correct. So that's what we are going to do. Let me first take you through this federated everything algorithm, right? So you have a server, all right? Select a random subset of clients. So are you are the server, right? Now you have an option. You have an option of calling in or choosing. You have your app installed on, say, a million users, right? So you want to select a specific random subset of users from them, right? uh, you send the current parameter theta t, is what they are calling it, to those random subset of clients, right? Now what you do is you sort of ask them to train it and run some number of SGD steps on top of that particular old model, and return the changed model to the server. So now this is no different than exactly this. So you chose this a 1 2 3 4, say some 10,000 clients basically, okay? And you chose these 10,000 clients to sort of uh, I'm sorry, I was getting a call, so broke my continuity. So you chose these 10,000 clients to run the next set of updates. You ran those updates, you collected all these new weights, basically the changed weights basically, and what did you do? You averaged it across and added that net averaged weight to the original weights that you had actually sent across, right? In that way, what you have now? You have a new model, right? And then what will you do? That's very interesting, isn't it? Then what will you do? Very simple. You repeat the same cycle over and over, either with the same set of clients if they are happy ones, or with multiple such random sets of client over and over and over again, so that you will have a new version of this particular model, right? Now that you have some particular version of this particular model ready, this model then becomes the purple one. Now purple one is actually pushed across, and you go with those kind of iterations. Did I confuse you completely? Have I lost you? Okay, so there is a question. Averaging of weights of individual models or parameters may help to create a global model. Yeah, Madhura has perfectly sort of gotten it before I actually explained it out to you. If you have any questions despite that, do let me know. We will discuss. All right. So it is very simple. It's like you're like my uncle, right, had this very interesting way of watching a cricket match. He would ask everybody that he would know, how much India will score today, how much India will score today, and he will collect. He would give his number that, yeah, today I think because of XYZ reasons, our score will not go more than 250, right? And he will then take the scores from all these clients, and then based on the difference between what he gave as the seed and what they are saying as the response, and the difference between them, average difference, he would then update his own prior. So that is the way in which one should think of this particular paradigm, right, working. Okay, so now you have this new estimate which you can again pass through the same cycle that we have passed through and keep getting better at it as we go along. One very, 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 very crucial question: can sharing parameters with the server also lead to privacy leakage? Definitely. If you don't do anything about it, there is a lot of potential of abuse even then. But tell me, Amit, let me twist this question back to you, right? Sharing the data as is vis-a-vis the parameter, do you think there is at least a layer of obfuscation there? I am not claiming that it is safe. I am not claiming that privacy is preserved just because the data is not being shared, only the parameters. However, there is just one sort of obfuscation in place, right? And when we talk about differential privacy in the next sessions, as we go along this journey together, we will understand how using the concepts of differential privacy along with this federated mindset, we will be able to safeguard privacy as well as do this distributed kind of learning and solve the problem. I hope I sort of answered that question there. I know that I am using some loaded concepts as well as jargons like differential privacy, etc. But you have to take my trust. I mean, take me at my words. We will discuss those not today, but the next time, sometime next, when we meet, basically, next time when we meet. And I hope you are okay with that. Yeah. So with that, with all of that in mind, let's also sort of call out certain important differences between what we have seen in this particular paradigm of federated learning vis-a-vis what we what everyone else does in a standard machine learning flow, basically, right? One of the most striking differences in the data side is it is massively decentralized, and therefore there will be non-IID partitions. Can someone tell me what IID is and why is it important? Okay, leave aside why is it important, but what is IID? Independent and identically distributed, right? I love to throw these jargons around. Well, it is just to say that each individual is unique, and therefore whatever they do will be highly correlated to itself and uncorrelated to everything else. Correct? And therefore it has a potential to cause problems in learning, basically, right? That's something that we should be taking away from here, to keep it very simple. Okay, what happens therefore is, because things are IID, because because it is so away from everything that we know, there are no statistical guarantees that the results that we are getting out of the algorithm which we just discussed, the federated averaging algorithm, right? Those are not there is a very real reason for us to worry about that. Those are not representative results, right? Those are either overfitted, underfitted. There can be 1,000 shapes and sizes of problems with those results. So that is one problem which is out there. Like, mathematically speaking, nobody would be able to claim that here are the error bounds, here are the nice, here is the nice theory why this whole approach will work out, right? There are some real issues there. However, the same set of guys, McMahon and everyone else at Google, have proved it by deploying it in apps, which we will see as we go along, right? So, while it is a real danger in terms of the, how can we trust an algorithm if there is no, sound mathematical basis for it? Well, if that were the core concern today, AI would not have been where it is any which ways, right? So yeah, I mean, you have to take sort of experience of way advanced experts than I, and say that this by and large works for a certain set of problems, right? This federated learning algorithm and federated learning paradigm by and large works for certain set of problems. That's all, right? However, there are other issues as well. The data availability is limited in terms of time, and there is a time of day variation. What does it even mean, right? It means that if I'm using my mobile, I would not like such kind of heavy duty learning cycles running on that mobile. Are you with me? Would you like that the mobile is doing a heavy duty computation? Because when that thing is doing some heavy duty computation, you get to know it gets heated up, it loses a lot of battery, correct? So you want it to happen only when it is charged, it is kept without anybody touching it for a very long time and stuff, where the battery is quite a lot and stuff like that. There are so many constraints there, right? So those are the real things which come into play here in federated learning, which you will never ever see in any other type of learning, correct? They are unreliable for that matter, right? If there is a fluctuation, even if training is completed, the data may not be actually sent across. Then what will you do, right? So there are so many such kind of small uh, thorns in the entire process potentially, that the only way it will work out is when you are doing it at a huge scale, right? Just remember that part and let's keep moving. So this is how it looks like, right? These are the learning cycles, so to speak. What do I mean by cycles per se? Well, of course, this particular first cut of model you have published, you have collected the first cycle of the thing from, say, East Coast when they were sleeping, right? And after a few hours, or if you have a customer base in Australia for that matter, right? So from there you do the second cycle, right? So you keep sort of you keep sampling from various time zones, and that way you keep generalizing the model as much as you can across the times and across the time zones and across the habits across the globe, right? So it is going to be a truly global model, so to speak. So let me just quickly check the questions if there are any so far. uh, so question is, wouldn't it be better to segment users based on certain criteria and then sample and push the combined model to devices instead of stochastically choosing them and providing the same model globally? Well, that's a choice that you would practically make proactively. Why? Think about it. The okay, which brings me to sort of the next small topic as well. Can you guess which is that Google app which has implemented federated learning? Anyone? It is. I'm sure you guys know about it. I'm sure you guys will be, commenting about it. But there is a delay between you comment and I get those comments actually. So basically, the name of that app is Gboard. Gboard is nothing but the keyboard that I get when I actually try to type anything. Okay, so that is the real implementation of this particular app, this particular federated learning algorithm. Okay, the point that I'm trying to make therefore is, Dipanshu, he has asked that smart question, that why to have one single model across, you know, across the entire globe? Why not segment the model across according to the some strata of the population, and release that to only that strata and keep such models local to local strata? And it makes sense for Gboard, isn't it? The kind of jargons that individuals would use, correct, uh, would differ from India, where we type in Hindi but use English as the mode of communication. Like, मैं क्या कर रहा हूं, I literally type MAI space KYA space KAR, etc. Right? So, are those in English words? No. Is there any lexicon or dictionary which contains these words? No. Then what to do? Introduction of new words by using machine learning itself or federated learning itself is one of the cornerstones of Gboard actually, right? So what they have done is they have kept release and training of the model pretty much local over there. The kind of words that will be suggested to you based on your keystrokes in India will be very different than what they will be suggested to you when you are in the same person, by the way, right? Same person is in Australia for a longer duration of time, right? The model, the incoming model should change. Otherwise, there will not be much of a difference, right? Because inference itself is happening on your device at the end of the day. See, that's the whole crux of all the talks that I am interested in, right? I am talking about inference on devices, inference on the edge, correct? So that's where this whole thing is, going towards, right? So thanks for that question, buddy, and I hope I have done some justice with it. uh, okay, there is a question around slides and recordings, and I am sure there is a standard way of getting around this particular question, so don't you worry. I mean, we will do all of it as we go along, right? So by the way, Gboard, as I mentioned, so what all things it has already implemented, per se, using federated learning. It powers up the prediction strip when you type or swipe. I am a big fan of swiping for typing, right? So when I swipe on the Gboard, I already get the predictions that I am typically going to use the words for in my prediction strip. So that is coming thanks to this particular RCNN model on your device, right? Which is trained thanks to this modality of federated learning, right? Emoji prediction, that okay, given the sentence so far, which emoji am I going to use, right? Action prediction, new word discovery, like consistently, if I have used certain word which was never seen, COVID-19, have you ever used that word before? I don't know. I mean, if you are woke and if you are very aware of your surroundings, you would have started using it maybe from December 2019. But if you are anyone like me, not before February, right? So how will you introduce that in everybody's jargon, basically everybody's mobile, the same way, exact same way, right? So that is all beautiful work that can be done using federated learning, and has been done and tried and tested and proved by Gboard app. Another place where they have used this functionality is Pixel, right? For all the settings that are there in the all powerful Pixel camera, which are the ones that typically people end up using, right? How to, I am all thumbs when it comes to technical settings of a particular camera, right? How to make empower me, given a particular context, to sort of capture the right photo with all the right settings. That auto setting thing happens by federated learning, right, in Pixel. So I know I am running very close to the time, so let me leave you with these two things, and possibly we will not have the time to discuss anything more in detail, but so be it. I hope so far it has been entertaining and useful for you. How to get stuff done, all this is gyan, I totally get that, I am with you. What are the on ground level frameworks which allow us to implement federated learning as a concept, right? There are two. One is our own TensorFlow Federated, right? TFF. Now, TensorFlow Federated, to me, and this is coming from a practitioner who is not that much involved in AI on edge, from my work perspective, very clearly, right? I found it to be a little more sort of lower level implementation, right? It has federated core, it has federated computations. There are so many ways in which they have tried to make it simple. They have thought it through, and there is a good roadmap for it. However, let me also do justice with another of my favorite frameworks, which is called PySift. There is an organization named Open Mind, not MIND, MINED, right? And Andrew Trask runs a course on, I think, Udacity, which talks about federated learning and privacy preservation. And it's a wonderful course, and you should just have a look at it. Open Mind is a wonderful org doing good work in privacy preservation side, and PySift and PyGrid are two such packages which provide you the entire backbone for deploying such kind of solutions, which utilize all these federated principles as well as privacy preservation principles, and allow you to sort of solve problems at scale, right? So these are two options which you can take back right now and try to get yourself involved in. And these are just very raw and very new sort of avenues to explore. So I really, I would not say in any shape and form that I am expert in any of this, but even I am exploring just like you. So we can go on that journey together, right? So with that, let me just check if there are any other interesting questions on the board. If there are not, I think there are a few things that I wanted to give you and leave you with an example, but I think it will be too crammed up in time. So let me just take up any questions if there is, and take it forward. So let me just check. So if I am a new participant to Gboard, with my iterations of federated learning already conducted with many users, right? Won't it force me with its predictions? Does that mean it's better to be early part to the Fed? Okay, I hear what is being said there, right? So the concern is, if I am not part of this federated learning iteration, my predictions will never be, my utilization will never be captured, and it is a real worry. All you have to think about is, hope that whatever way you spell your spellings, as an example specific to Gboard, others also spell the same way. If the kind of mistakes that you make are made by others, your Gboard will suck equally. If you are any which ways not making any mistakes, if you are using the vocab which is any which ways commonplace, you don't need to worry about it anyways, right? So see, that's maybe it's very interesting segue. I will leave you with that. The very fact that an individual need not be compulsory in the sample to influence the quality of the model gives you away the very basic fact that privacy of that individual is preserved. There is nothing special that he or she can sort of contribute to the model, which will sort of betray his own private identity. Correct? With that, I will leave to it, and possibly segue to the next talk that we will have together. uh, Oh, so by when do we think that the federated learning be used to build end-to-end products? Gboard is an end-to-end product, so Google is using it, right? Apple, I think, is using it in their own products, for that matter, right? So it's not something built of dreams. It is very much tangible and real in front of us, right? Okay, cutting very close to the time today. Thanks to the TFUG and all the sponsors and so many people taking all the pace to align all these events together. Thanks everyone. Thanks Usha for involving me. And we have this entire 3-course meal for you, right? The first one, I was just an entree. There is a main course, and there is then a great dessert for you. So with that, I will thank you for being patient with me, listening to me, and I will hand it over back to TFU
Yes,
guys.
sir.
Thanks.
So, can you hear me?
Yeah,
So I guess this video is going to be recorded, and it'll be there on YouTube, and people will be watching this video later on. And what happens is, people might post comments and all that. So I hope you could spare some time and address these questions from these people.
I'll do that. Thank you.
Okay, sir. And thank you, sir, for this informative session.
Pleasure
And
in mine. Thank you.
and just like you said, yes, we do have a starter, main course, and the next thing. And yeah, for coming up next, we have a young and a very talented person. His name is Rishit Dagli, and he's going to be talking about hybrid quantum classical models using TensorFlow Quantum. And I guess we can start with him now. Rishit, can you unmute yourself? I guess there's a bit of an audio problem. Just a minute. Rishit, there's a button called mute and unmute. So can you try clicking on that? Hi.
Okay, so can
Yeah,
you
we
hear
can
me?
hear you. Yeah, we can hear you now.
Oh, it seems there was a mic issue, so I tried joining in again, and as
Yeah, that
as
happens.
always, magically works. Okay, so let me get started. So before I start with anything at all, um, I have switched on captions from my side. You will see them down over here. Yeah, you can maybe even see them now. So you would not need to switch them on from your sides. Um, uh, yeah, I don't know that much of Kannada, though I've written TensorFlow in Kannada over there. Yeah, that's for you to understand. So hi everyone, thanks for coming here. Uh, and a bit about me before we get started. I'm Rishit Dagli. You probably just read that down on the slide. Uh, and I'm currently a grade 10 student, a TEDx and TEDx speaker. And a part of the things listed down over here, I have often represented my country and also won a few international level hackathons and competitions too. And guess what? I love to conduct research. So I've also written 7 research papers in all about AI and robotics. So yeah, that was about me. And while the session goes on, feel free to leave any questions you have in the chat. The team will constantly be telling me the questions that come over in the chat, and I'll be looking them over too. So be sure to do that. Any reactions, any questions, put them over in the chat. Okay. So with that, let me just tell you who the ideal audience would be for this talk. So it would majorly be people who have worked with some deep learning models and even made a few. So it doesn't matter if you have built a deep learning model with Keras API, which is a high level API. You don't need to know the maths which goes inside, or made one using the C++ API, or even the TensorFlow estimator. It doesn't matter. The talk would still make sense to you. So even if you know Keras, you have come in the right place. And we'll talk about quantum AI and quantum computing. So, and of course, developers who are eager to learn about what quantum computing has to offer, especially quantum AI algorithms, and how do I exactly use this in the field of AI? How can it help me? So I would also like to make it clear that I don't assume any background of high level physics and maths from you. So no need to worry. You should not be a PhD pursuing person to make sense of this stuff. So let's just go over and brief about what we'll be discussing today, the agenda for today. So we'll start with a gentle introduction about quantum computing, the motivation behind this, see a bit of TensorFlow Quantum and how it can help us, and then go over to some demos which you can try out for yourself too. So you can try out all of these demos in Collab itself and have fun with the demos too. So yeah, that will be all about what we'll be covering today. So let's start by talking about a few terminologies about quantum computers and quantum AI in general. What are they? Why are they even different from a machine which you have at your home? Why is a quantum computer any different from the one in which you are watching the stream, watching me right over here? So, if this was some other topic, I would actually first tell you the motivation behind it, about why is it even worth the switch from a normal computer to a quantum computer. But I think for this particular topic, it makes more sense to introduce some terms first. So let's go ahead and do that. So we'll start from the start from the bottom. So take any machine around you, maybe the laptop or mobile on which you're watching this. So as you might be knowing, simple high school or elementary school thing, computer works on ones and zeros. We all know that, right? Binary. A computer understands ones or zeros, and that's how I make up all the information I have. So what that essentially means, it works on ones or zeros, is if I have a bit as in the smallest unit of storage in a computer. Just going over a few older things and uh, a few older terms like bits to kind of give you a refresher. So if you have a bit in a computer, in a normal computer, it can have two values or two states, as I can tell. So my bit can be either 1 or my bit can be 0. All with me till here? Nothing new till now. A bit can be 1, a bit can be 0. In a quantum computer, you have a bit which is now called a qubit, or as I say it, a quantum bit, often referred to as a qubit. So, a strange thing about this qubit is it can be 0 and 1 at the same time. So, how is that possible? Are you telling me 0 is equal to 1, because it can be 0 and 1 at the same time? No. So we'll talk why this makes sense and why are we even going from representing our data. And I'll be talking about a bit more of the machine learning side of it. So representing our data not as ones and zeros, but as a qubit, which can be 1 and 0 at the same time. So first let's break it down to make some sense. So if I measure the value of my qubit, I will get a specific value, which will be either 1 or 0. So once I measure my qubit, I get a 1 or 0. Or usually the most classical example, I get up or down. Up is 1, down is 0. You can take that for now. But before I measure my qubit is what I'm concerned about. So before I measure my qubit, it can exist in both states, up and down, with some probability. So in this example, you see that um, up has a probability of 0.7, and down has a probability of 0.8. Just an example, nothing new over here. But a qubit in this state has probability of both up and down at the same time. So it exists in what is called a quantum superposition, and quantum superposition is a state where your bit can exist in both up and down with some probability. So super simple till now. We'll not go very deep into this. You actually don't need to go very deep into this to start building things with TensorFlow Quantum. But if you're interested, I could always kind of help you. Now, this might have got a bit confusing at this stage, making a bit go up and down at the same time, go 1 and 0 at the same time. But hang on with me. You'll soon know how is this even helpful to us at all, especially for machine learning. So now that we know a bit of the basics of it, basics of quantum computing, let's see how this all comes together. So let us take an example. I have 2 bits. So I want you to calculate how many combinations can you make with these 2 bits. I'll give you a moment to think this through. So remember, bit means either 0 or 1, and I have 2 bits, which means I can make 4 possible combinations. Simple, right? A bit can be 0 or 1, so I end up with 4 possible combinations: 0, 0, 0, 1, and so on. So let's say I want you to tell me which of these 4 numbers I have chosen. So let's say I have a data point in my data set, and each data point is made up of just 2 bits for an as an example, and I want you to know what is the number. Then what do you need to what do I need to tell you so you can predict the number accurately? You need the first digit of the number, which is either 0 or 1, and you need the second digit of the number, that is again 0 or 1, and that's it. That's a classical computer. With 2 bits, you can make 4 combinations. But if I want to know the number, but if I want to know the information stored in a quantum computer by 2 qubits, you might remember the superposition that we talked about. It can exist in 1 and 0 with some probability. So to know the number by 2 qubits, I need 4 coefficients, or let's go back to that linear regression thing. I also want you to think it this way. When talking to machine learning enthusiasts, it kind of makes more easy to explain it in this way. Um, so I have 4 coefficients A, B, C, D, let's say. So we just saw how 2 qubits can actually contain information worth 4 classical bits, because I now also need the 4 coefficients A, B, C, D, which are the probabilities, right? So I need the so I can so I have 0 and 1 with some probability. I also need the 4 coefficients A, B, C, D, which will tell me the probability. So I just saw I still have 2 qubits over here. Qubit. So I still have 2 qubits over here. But you just saw how it actually takes me four it actually contains net information of 4 classical bits, right? So let's kind of scale this up or expand up in this manner. I just showed you where a classical bit uh, uh, where a where how do I explain this? Yeah, where 2 classical qubits actually hold 4 bits of information, and 3 classical bits would actually hold uh, oh, 3 qubits would actually hold information worth 8 classical bits. So if I just apply a bit of math over here, I can easily see that if I have n qubits, I actually store 2 raised to n bits of information. Now, that is something really wonderful. So, where a normal computer can hold n bits of information, a quantum computer would actually hold 2 raised to n bits of information. Now, isn't that kind of cool? So just saying you have 100 bits, 100 normal bits. So let's take an example for this. So let's take the 300-bit example. I have some cool stats over here. So uh, let me show you the power of this. So 300 bits on a normal computer is not even enough to store an image, right? You can't even store an image in 300 bits, a good image. But with 300 qubits, which is equal to 2 raised to 300 normal bits, that's the number of particles in the universe. And yeah, that info is not created by me. The stat is not created by me. So you can't trust on it. So isn't that cool? The power of qubits, how you can store so much more information with them. So that's why I want to use this idea in machine learning, where I have huge models. I want to share more information, and that's how quantum computing actually might play a role in machine learning. So at this stage, I'm saying might play a role in machine learning, and we'll soon see how it can actually help us see how it makes things so much faster, makes easy to work on complex problems and things like that. So now that you know the basics of it, you know why should I even care about quantum AI or quantum ML, use quantum computing in machine learning at all. Let's see how this uh, so you just saw why it contains more information and how it can maybe be advantageous. We'll see how you can actually use this idea in ML in practice. So we'll be building hybrid quantum classical models. If you remember, that was the title of my talk. So let's see in the first place what hybrid quantum classical means, and why do I even want to build hybrid models in the first place. I told you a qubit contains more amount of information than a normal bit. So why do I want to mix hybrid and quantum? Why shouldn't I just use quantum computing to build my AI application? Let's see that. Let's see that in the first place. So, a very common misconception at this point is that quantum computers can replace the computers you currently use. And I assume most of you might at this stage have this kind of misconception that I should just use a quantum computer or some quantum algorithms for my machine learning task or for day-to-day things. And yeah, that would be great, right, if I can store so much information. But the twist is it's not indeed faster for all kinds of operations. You're streaming this talk right now. You're listening to me. You're hearing me right now. With a quantum computer, that would not be faster. In fact, operations like streaming, maybe a video or multimedia files, would in fact be very slower with a quantum computer, so, or even reading data. So, what do you do now that I told you that a quantum algorithm or a quantum computer might actually be slow in some points? What do? You use quantum and classical computing together to build better, faster, and more complex applications. So, by more complex applications, I mean applications which can work with more complex data, work to get more complex information from the data, is what I mean by more complex applications. So, you can kind of use both quantum computing and classical computing to build better applications, and that would be the goal about how you could do these yourself. So now I guess that now I guess you know why should I use a hybrid model that's use both classical and quantum computing to build a good application. So, you know about quantum computing, how it works, how it can play a role in building AI application. Let's look at what TensorFlow has for us and how TFQ or TensorFlow Quantum can help us in doing so. So, if you're not aware, TensorFlow Quantum was just launched at TensorFlow Dev Summit, so it's pretty new, and a lot of work is actually going on. Things are coming up, new things are coming up. So yeah, it's just something good to know. It's recently launched, and new things are constantly coming up. So I think this is something universal with TensorFlow. It makes development. Uh, so this is something universal with TensorFlow. It kind of eases your machine learning tasks. So even when you had the TensorFlow estimator API, you essentially said, I want to abstract all of the things like how to do forward propagation, how to do backward propagation from my main machine learning task. So I can focus on writing the real application instead of fixing problems in back propagation or saying, oh, I have a problem in this operation is not working. I don't want to do that kind of things. I want to build better applications and lowly, abstract away those mathematical operations. So yeah, it's something universal with TensorFlow. Keras took it to another level, abstracting even more things, making it easier for you. So what TensorFlow Quantum does is it makes development of these kind of hybrid algorithms. So I'm specifically mentioning hybrid algorithms a lot easier for you. So how does TensorFlow Quantum make it easier for me? With TensorFlow Quantum, you can still train your models with standard keyless functions like fit and compile. So you did a model.fit with keyless, a model.compile with keyless, specified the loss functions and optimizers in the model.compile. You need to make a few changes, allowing for data to be ingested in quantum state and about using quantum algorithms, and we'll talk about that. But it's really cool to know that I can still use keras, which maybe all of you already use and have worked with. I can still use that with TensorFlow Quantum and make and build better applications. So that's something I really love, that you can still use keras. As a programmer, I don't need to learn something really new, something out of the box. I can also use the estimators and keras just for this. So let's now take a look at how do you actually bring this out in practice and build models. So, first, let me tell you about the process you would follow to do so. So the first question you might have at this stage is, at this stage would be, how do I represent my algorithm on a quantum computer? So a normal algorithm, I just write some code, it gets translated to ones and zeros. But how do I actually represent my algorithm on a quantum computer? So you use something called quantum circuits. And this is exactly what TensorFlow does. It integrates a tool called Circ, which allows you to make these kind of circuits or the quantum algorithms. So these kind of circuits, or as I would say at this stage, quantum algorithms, are just simple operations you do on qubits. So a normal program would do some operations on bits. With these kind of circuits, you do some operations on qubits. So TensorFlow Quantum integrates Circ, which is another tool by Google to easily build these kind of quantum circuits, and TensorFlow to build hybrid models. So Circ plus TensorFlow, uh, it tightly integrates Circ and TensorFlow to do so. So let's see, uh, um, let's see how a quantum circuit actually looks. So each of these qubits, which you can see over here, each of these qubits, the horizontal wire in this circuit diagram, and each are qubits, and each of these boxes, the a box which you can see right now highlighted shows B, that's actually a single operation on a qubit. So the horizontal wire is a qubit, the 0, 1, 2, 3 is just a qubit, and the A, B, or the squares which you see over here are operations on the qubits, also called a quantum gate. So with Circ, you can code circuits like these very easily. Let's zoom out a bit and see a high level overview of this. So this is a diagram showing you how all of this comes together. What I want you to take a look at is the first process, which is you prepare a quantum data set. So your data passed to the model should be quantum data. So first, let's take a look at main part, building a quantum algorithm, or also called a quantum circuit. So that would be kind of the major part which I want to do for my quantum AI application. So the installation part for TensorFlow Quantum is pretty straightforward. So what we'll do is we'll not waste time over the installation part and how you can do it. You can find the details about how to install TensorFlow Quantum at this URL. So I'll just pause for a moment, allow you to take a note of this URL. So I think you might have taken a note of this URL about how to install it. Something pretty straightforward. You just do a pip install and things like that. You have all the details about it right at this URL. So remember me telling you that Circ makes it really easy for you to make circuits or program circuits. Here is how you define two qubits. So I just defined two qubits, Q0 and Q1. I defined two qubits, and let's put them in a circuit. So so you make what's called a circuit object to do all of this for you. So here I make a simple circuit with just three operations, or also called three gates. And here you can see I'm also mentioning I want to do the operation on qubit Q0. So I'm doing some operation. For now, I'll leave it just some operation on qubit Q0. I'm doing some operation on qubit Q1. So yeah, that's simply how you define a circuit in SOAP. And here is how my circuit looks. Again, remember the two horizontal wires are my qubits, and the boxes you see over here are are just my operations, or also called a quantum gate. So you can understand it as three operations, which is Rx, Ry, and a not operation. So so this thing right over here represents a not operation, and this is essentially how you would also build larger circuits or larger algorithms. Uh, so we'll see this in a great detail and how it can actually be used together with Keras. But as of now, you can see with just 3 lines of code, I made a simple a simple quantum circuit with 2 qubits. So that's a bit of how SERP makes it a lot easy for you to do this kind of stuff. So now you know how to code circuits, how circuits work. Uh, so let's actually see them in an end-to-end AI algorithm. Let's do that. Let's first look at a few things which TFQ or TensorFlow Quantum provides us to build these algorithms very easily. To easily train your models, you need to, of course, support differentiation, right, of quantum circuits. Can you just think about why do I even need to support differentiation of quantum circuits, and how do I even differentiate them? I'll give you a moment to think this through. So, if you remember very basics of how maybe, let's say for an example, how you do gradient descent, simplest of the simplest, how you do gradient descent. So major thing right over there is your loss functions should actually be differentiable. So we have a lot of times where you don't actually need this, but for now, there are methods that you can do even when you don't have your loss functions to be differentiable. But for now, we'll take the simple approach, that is my loss function, that is my quantum circuits in this case, should be differentiable to support hybrid backpropagation. So TensorFlow Quantum helps you in doing so without you having to worry about the internals of it. We also want to be able to generate quantum data on the fly and train huge amount of circuits in parallel. So though this may not seem like a big thing, training a lot of circuits in parallel, but it's good to know that TensorFlow Quantum also supports this. You can have a huge number of circuits running in parallel. Uh, about the part that I want to be able to generate quantum data on the fly, it's essentially very useful because a simple strategy is I want to have quantum data when my CPU or a normal computer requests for quantum data. I want to have it available. I don't want to keep it idle. So TensorFlow Quantum again ensures that. So this may not, so the easy switching part may not be of much use now. We'll be doing things today in a simulator, in a quantum simulator, and you'll probably do so until quantum computers get cheaper. But there are very minor or almost no changes when switching from a simulator to a real device or a real quantum computer. So again, this may not be of much use now, as we'll be doing things in a simulator, in a quantum simulator. So, but we just saw how to make a simple circuit with Circ, and TensorFlow Quantum is closely integrated with Circ, and it works seamlessly with Circ. So you can use Circ circuits or the algorithms generated by Circ in your TensorFlow as a layer. So in a model, I have a layer which is actually my circuit. So I can easily do that. We'll see how you can do that. So the foremost thing to know is that all circuits which you generate with Circ are essentially just tensors. Yeah, you heard me right. The circuits you generate with Circ are essentially just tensors. I feel this is like an additional benefit you can get with TensorFlow Quantum. So, while so as I just mentioned, while using hybrid models, that is some using using a quantum AI algorithm and a normal AI algorithm together. A normal AI algorithm would, of course, work with tensors or numbers only. So I need to have a way to change my circuits into tensors. And again, TensorFlow Quantum has you covered. We'll see how you can do this and how you can convert your circuits into tensors yeah, in some time. But yeah, TensorFlow Quantum allows you to do this too. So you can easily build your hybrid models. So TensorFlow Quantum converts the circuits you have into you have to the classical data, which may be a web application or Android application, depends on the platform where you deploy, can understand. So I want to make my end platform, which may be a web app or Android app, to understand the data I'm working with. So I don't want to output quantum data, which it may not be able to make sense of. So I want to output classical data, which I can actually use in my application, which can be of some use to me. So uh, so it's essentially just running and simulating on Circ or any other simulator can be used with TensorFlow. But we'll be sticking with Circ for today, and also Circ is closely integrated with TensorFlow. So you can have the simulation of Circ as an operation in the DAG or dynamic acyclic graph created by TensorFlow. So again, I'll not go into jargons. You don't need to know what's a DAG if you already don't know about it, but you can just understand that uh, the simulation of Sur can be an operation in the TensorFlow graph. So the TensorFlow graph, for those of you who are not aware about it or don't know about it, is just in simple words a sheet through which, okay, so this may not be the most accurate one, but enough to or to give you a good understanding. It's like a program sheet which TensorFlow goes through while execution, and it has all the operations I need to do, like maybe multiply two matrices and things like that, or do a dot product, multiply two numbers, everything. So the simulation of SOR can also be an operation in the graph created by TensorFlow, which will then make it easy to give the end platform the kind of data it knows about, classical data, which it can make sense of. So let's come back to this diagram you started with: quantum data preparation and evaluation. And once you measure it, it becomes classical data, and you can feed it to a standard neural network. So what I'm saying is, once I measure my quantum data, as I said, a qubit can either be 1 or 0, but as soon as I measure it, it will be any of 1 or 0, not something with probability. So as soon as I measure my quantum data, it can be passed to a standard neural network. And from the output of the standard neural network, the loss functions, the loss functions parameters of both the classical and the quantum model can be improved. So now you can see how a hybrid model essentially works, with both a classical and quantum model working into place. So I'll give you a moment to kind of go through this, and give you a short overview about what we did till now, so you can get a better idea of it. So just like a quick refresher, you 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 have some quantum data which is being prepared by your quantum circuit. You pass it to a standard neural network, which and from the output of a standard neural network, we can improve the functions, you can improve the parameters of both the quantum and the standard neural network. So so that was actually how it works behind the hood. You can you can do the implementation with keras itself, uh, have the quantum part as a keras layer. So remember me saying that TensorFlow Quantum makes it simplified for you to make quantum AI algorithms. We talked about that, but now you'll see how it actually makes it simple in code. So how easy it is for you to code a quantum neural network in code. We'll see how well it integrates with keras. So remember, you did this part before. You had a circuit with source. It can literally be any circuit. This is um, just the three gate circuit we talked about. But let's change this to make it a bit more generalized. So now I have a quantum circuit with any number of gates. We can literally have any number of gates. What I now want to show to you is how to create this as a layer in your keras model. So, wha- so I'll make what's called a parameterized quantum circuit, usually referred as PQC. So just a big name, nothing to worry about. So I'll pass it the circuit, which is here called Q circuit, and make a PQC layer which can be used with the keras model itself. So this thing which you see, tfq.layers.pqc, this part can be used with the keras model itself. So the soap.z qubit is, so this is just a qubit on which, so the qubit part, sorry man, yeah, the qubit is, so the qubit which you see over here is just the qubit on which I want to perform the op. Thing to remember is, we talked about this in brief. You should then pass tensors into your standard neural network, because a standard neural network will be clueless if it sees quantum data. It just understands tensors. So again, you just call the convert to tensor method from TensorFlow Quantum, and this part is taken care of for you. The the PQC layer is actually now converted into tensor representation. Then I can pass that right into my model. I can pass the tensor data, right into my PQC model, the model I just created. And that's essentially how you go from a circuit to a functional layer. So enough of talking. Let's see this in action. Yeah, let's get to the demos part. You can try out these demos for yourself in collab itself. However, I'll be showing you all of these demos here on a GCP AI platform notebook, so we can kind of do it faster right over here. And um, yeah, we can do it a bit faster right over here, right in the demo. You don't have to wait long enough. So but yeah, the notebooks made for this talk can be used in collab itself. So here is the GitHub repo for this session. I'll let you take a screenshot or take a note of this. The GitHub repo has all the notebooks made for this talk. So this also has all the demos for this talk. So go over to the GitHub repo, and maybe after this talk, try out these demos for yourself in collab itself. So I'll give you a moment to quickly note this down, or take a or take a screenshot of this. So I guess you might I guess you might have done that now. Yeah. So I'll quickly switch my screen, and we'll go over to the demo screen, and we'll try out the demos right here. Remember, you can also do this in collab. Just go over to the code repo. I'll just switch my screen pretty fast enough. Um, yeah, uh, I have switched my screen. So let's see if the new screen is visible. Yeah, it's visible now. Okay, so I'll just zoom in a bit. Yeah, this should be visible enough now. Okay, so here's the GitHub repo, which I talked about uh, for this talk. You can view all of the demos which I do over here, and they are a bit different. I would say quite different from the demos or the notebooks which are provided on the official TensorFlow website. I have simplified these notebooks down for you. I've uh, I've simplified these notebooks down for you so that you can kind of um, do more with it, understand the code completely. So I'm running this not in collab, so I'll just skip the collab specific things, and let's try out this in action. So what I'm doing right over here is I'm making a qubit and placing the qubit. So just placing the qubit on the grid. So for this example, what we'll do is we'll take an example that I have just two labels to predict, which is 1 or 0. Just a dummy example, just a dummy algorithm to make more sense of it, so that you can then try it out. We'll also work with real data right now. So but an algorithm before that, so you can get a better hang of it and how to use TensorFlow Quantum. So I'll just put in my expected labels, which are two labels: label 1, label 2, one hot encoded. So this is I'm just randomly rotating the axes. So it's okay if you don't completely understand this at this stage. But what I do want you to understand is making the circuits. So yeah, so remember we talked about circuit and how you can make a circuit with it. That's exactly what I'm doing right now. Here I just defined a random angle between 0 to 360 degree, and here's the qubit on which I want to perform that action. So if you go up right over here, you see I've defined a qubit over here. I'm telling so I want to perform that operation on this particular qubit. So I'm making two circuits right over here. So let's wait for these circuits to be made. And also note that I'm converting them to tensors. So I remember me telling you, you can easily pass them to standard neural network with tensors. So tfq.convert.tensor uh, helps you again. So let's go ahead and visualize these circuits. So this is some. So remember that the angle was some random number between 0 to 360. This is a very simple example. So I'm adding some noise into the example, and yeah, just a hard coded data set so you can practice with. So this is just some random number. So this number might change. Let's run it again. 1 - 1.73. Yeah. So you can see that it changed from what I had previously. So let's come to the most important, or I'd say most interesting part, which is using this in with Keras. So how do I take my quantum data as an input? I simply use tf.keras.input, and I can create a quantum model, which is again a circuit. So I can, so just as the example I mentioned in the slides, I have the quantum model and I pass it into a PQC layer, or a parameterized quantum circuit layer. Uh, Parameterized quantum circuit. Sorry, not the layer. Uh, so I would not call it a layer at this stage. So I can just pass the circuit we just made into the into the PQC. So I can then start getting outputs from it right over here. So I can also do something like run it over my quantum data input. So if you see the quantum data input, it's just a variable holds which holds my inputs. So let's go ahead and run this. And here is where I add a classifier to it. So just two neurons in the classifier. So I want you to also see that I can now simply define this as a layer. So my inputs would now be the quantum data input, which I defined above. My output would be the classifier output. So let's see what the classifier output is. So you can see that the expectation output right over here is what I get back from my PQC, or parameterized quantum circuit. And I'm just using that with a with standard two neurons in a Keras dense layer. So I can go ahead and compile the model. And yeah, forgive me for the typo right over here. So, and I can just train it as any other by using model.fit. So let's train it for 250 epochs. It should be fast enough. So I can see output right over here. Yeah, great. It's pretty fast, just because I had two labels. So I can go ahead and try to plot my loss functions. Try to plot my loss function. So I can see that I have actually got, my model has actually done pretty well. So here I'm using the binary cross entropy loss function. You can also experiment with some other loss functions in this example, but I just had two labels, so I resorted to binary cross entropy. So while performing inference, I would again convert my data to tensor. This is just two circuits. I'll convert it to tensor again, and then pass my data to the model. Then pass my quantum data to the model, because what a standard neural network understands is tensors. So so what I'll do is I'll again convert my input data, so my test data to tensor, and then pass it to the model, and I can see me getting predictions right over here. So I can see this is probably a lot. This is a lot lesser than this one. So I take this label as the one which I need to use. So again, that's good for. Uh, so that's essentially how a simple quantum ML algorithm works. And yeah, we made a hybrid quantum ML algorithm right over here, and made it classify. You saw, made it train with standard keyless functions. So you could just saw how easy it was to do so, the interoperability with keyless, and that's how easy TensorFlow Quantum makes it. So I had another demo right over here, which shows you how to actually use all of this to classify MNIST, which is handwritten digits, uh, how you can use this to classify handwritten digits. So I'm running out of time. So what I'll do is I'll not run it live over here. As we are running out of time, you can go ahead to the GitHub repo and run it for yourself in Colab. So we'll essentially do the same thing. Like I'll just go through it uh, a bit faster, so we save some time for questions too. So I can just see here's my MNIST data. What I want to do is, uh, again, I'm just keeping two labels over here, which is label one, or number one, and number five, as we just saw how to classify between two labels. So uh, to make it easier to kind of do this for yourself, I'm just doing it with two labels. So this is just some visualization code, and just to know the number of images. What I'm actually interested in is my circuits. So I can see the part of, let's go down. I can see that I still have a trained TensorFlow circuit, which I'll convert to a tensor, and a test TensorFlow circuit, which I'll convert to a tensor again. And I can just use this again with keyless. So this is a slightly complex circuit we made for this tutorial, and I can essentially create my quantum model just similar to the one I made in the previous demo. I can make a circuit, and have it um, and convert the outputs of the circuit to tensors and pass it into a keyless model. So yeah, so you might see this highly familiar from the last demo. It was exactly the same thing which we did. I have the input keyless layer. I have a PQC keyless layer, and I can still use it with model.compile and model.fit. So I'm not interested in the accuracy for this, because this notebook was essentially made to run as a demo. It was made to run faster. So you can try working around the hyperparameters for yourself. I just ran it for 3 epochs, as you can see. So I have a high loss of 6.5. So yeah, you can try it out for yourself. I also so you just saw how you can also use it in for a real life data set. So sorry to, I think we are now out of time. Sorry for a bit delay. Um, yeah. So we talked about these two demos today, and here are a few key takeaways for you, which I'll cover quickly. We first talked about the basics of quantum computing, the motivation behind quantum computers, and why do you even need them. And then we moved on to why you should use hybrid quantum classical models. We then saw how TensorFlow Quantum and SERP integrate together to allow you to make easier to allow you to do easier experimentation and make models easily. And then we actually made a hybrid quantum classical model right over here. So here are a few of my social links, and while you do this, I'd also love to take any questions if there are any. So, are there any questions? Just put them in the chat.
Hello, am I audible?
Yes.
Okay, I think as of now there are no questions from the comment section. I guess there'll be more viewers later on, so I hope you could spend some time to address the questions from comment sections later.
Sure, I'll do that.
Okay,
Oh,
and thank you for conducting the session. Uh,
it's my
and
pleasure.
yeah, and coming up next, we have Ram Seshadri, who is a data scientist, and he's going to be speaking about automated data visualization and machine learning for faster insights. So I'll hand over the session to him.
Thank you.
So,
Yes, thank you. And I'm going to share my screen right now. So hopefully everyone can see it. uh, Application window. Okay, here's the application.
yeah.
Can you see the full screen? It's coming up
Yes,
right
sir.
now. Okay, good. All right. Thank you all for the opportunity. I want to thank the TensorFlow user group for inviting me and giving me this chance to talk about my favorite topic, which is automated machine learning and visualization. It's going to be a short introduction to the topic, and then I'll do some demos. We'll use Colab and Kaggle notebooks, so you don't have to download anything if you don't want to. Of course, you can work from Kaggle in the notebook environment or in Colab. Now, this is a question you get probably asked a lot if you're a data scientist or a data engineer or machine learning engineer in your company. Why is the data science team taking so long to complete a simple project? And this actually came to me when I was working at an investment bank from my frustrated CIO. He thought that everything could be done in a day or two or even a week because he's was used to seeing Kaggle competitions where you basically saw people submit answers in as little as a few hours. Now, what do you think the reasons are in the real world that it's taking so long for us to complete data science projects? I'll just take some answers if you want to mention them. So I'm going to try to say some examples. One of them is basically challenges with frameworks. The tools that we work with are also not very user friendly. Some of the data and code is still very raw, and you have dirty data, so it takes a long time to turn them into somewhat cleaner data. So this is where we are, and I wanted to share with you some of the challenges here. And so how can we make data scientists more productive? We kind of wanted to understand what makes data scientists be more productive. First, we want something that will give us faster visualization of our data. Second, we want some form of feature selection. In real world, your data may contain hundreds of variables, sometimes even thousands. And putting all of them into the model may not be a good idea, because you might have an overfit model, you might have a very complex model then, and a model may not be interpretable. So reducing features is one of the key tasks that we data scientists do. And third is automatic model selection and tuning. This is where most of the people have spent their um, time and money in buying tools that do automatic, hyperparameter tuning and model selection. This has become a commodity. So people are now moving up the value chain to automatic feature selection and faster visualization. The last is probably the most commoditized, which is you can take your XGBoost model that's been trained and serve it in with any of the cloud providers. They will happily host it for you, and you can perhaps start serving your predictions. Now, current tools that do all of these, or some of these, are very limited, because one, they're proprietary and expensive. So you wind up paying for these tools and you're locked into their technology. Second, they are black boxes, some of which are too complex to interpret what comes out of them. And third, there is very little reproducibility outside of the tool. You need to be able to, produce the same results as the tool. Then there is very little you can do, because you don't know all the things that the model does, the AutoML tool does, in order to produce those great results. So you are basically stuck with using the tool from end to end, and you cannot really take it outside of the provider. Now, we are here introducing a simpler approach to automated machine learning, and it's called AutoML. And to automated visualization, it's called AutoViz. And these two libraries are built to give you interpretable machine learning models fast. So AutoViz is used in faster visualization. AutoML can do feature selection and and also model selection. So what are these tools? These tools are both open source tools for producing faster time to insights. The design goals are they should be simple. I created them with a single line of code as being a goal, a design goal, and I think we've mostly accomplished that. Second, it should be available to work on any kind of structured data with no preparation required. The idea being that you spend a lot of time cleaning data, and I'll give you one example of a very kind of dirty looking data, and you spend a lot of time trying to clean it. And when you have 5 variables, 10 variables, 30 variables, it's probably not very difficult. But if you have 500 variables, 5,000 variables, and they're all dirty, or most of them are dirty, then you need an automated way to
So,
clean that data.
so sorry to interrupt.
Yes.
I guess the only a part of your PPT is being displayed. It's being cropped out when you go to full screen.
Okay,
So
sure.
I guess I would suggest you to stay out of the full screen.
So, okay,
Yeah,
sure.
so this is fine.
This is good. Okay, thank
Yeah.
you. And so if you want there's a lot of automation that I had spent some time doing this. And let me see if this is that's because this one is in Chrome. Sorry, is in. Let me try to switch to a different browser. Okay, so here we are. I'm going to share my screen, and I'm going to switch to the Chrome browser on the Chrome tab. And I'm now going to see if it is any better to present this way in a Chrome tab. Yeah, it's coming up. Okay, so with the Chrome tab, you get a little bit more control, and I'm hoping that everybody can see the screen, full screen.
Yeah.
Correct?
Yes.
Okay, thank you for pointing that out. So the second is flexibility. We wanted to be able to work on any kind of structured data. Now I've got the tool to work on unstructured data, like natural language programming. So you can see actually NLP being incorporated into the tool. Now you don't have to go outside of the tool when you have text combined with structured data like numeric variables, categorical variables. Now you can have text data, and it will be able to process it with no additional coding from your end. The only thing that it's not being able to do right now is image data. That's something that I've been thinking about, how best to incorporate images into structured data. So if we were to combine now images, structured, and text, probably the tool will be kind of a much more powerful tool. Incremental, when you can use this tool, whether you're a beginner or an expert, you can perform multiple experiments with this. And the next one is interpretable. You get clear explanation of the steps that it is taking, and it's reproducible. The good news about this is that it's going to produce the model and give you the outputs. It's going to show you all the steps it's doing. It's not a black box. You can see every step that it's doing, so you can reproduce those steps yourself. And extensible, it's now open source, so anybody can contribute to it. If you wanted to, you can take this code and modify it. And so AutoViz and AutoML were designed to make data scientists' job easier, and hope it'll do the same for you. So what is, where do they fit in the ML workflow? The number of things that they do, the number of steps they do is a lot. I'm not going to go into the details, but if you were to do pip install AutoViz and pip install AutoML, those are the only two steps you need to do. And it'll take the data, classify the columns, and if the columns are date timestamp columns, it'll add datetime variables. If they are NLP columns like text, it'll build an NLP pipeline and add variables based on the NLP pipeline to your model. If it is all other variables, which are numeric and categorical, it'll analyze the problem, it'll label in code the columns, fill missing values, perform min-max scaling, add polynomial variables, then it'll combine the time series and the NLP variables to the data. It'll then select the top features using XGBoost. It'll add additional features such as a clustering variable that's called the k-means featureizer. Then it'll add a stacking variable if you wanted to stack multiple models together, or if you wanted to ensemble them. And then it'll perform hyperparameter tuning and produce results. So all of this is done without you having to do much beyond just installing these two libraries and calling them. All right, so what is AutoViz? AutoViz enables you to automatically visualize any data set, any size, with a single line of code. Basically, if your data set is very large, it selects a random sample from the data, and you can set how big the sample you want it to be. Let's say you have a data with 1 billion rows, but visualizing all 1 billion is unnecessary, probably too time consuming. So you can take 1 million rows out of that data and visualize it. So in the AutoViz calling statement, you can set the number of lines you want to visualize. Let's say also you have 5,000 features. Not all features are important. Maybe you want to visualize only 30 features. So you can set the number of variables you want to visualize to be 30, and it will automatically select the 30 most important features out of the 5,000, and it will display the charts to you. So it first does a random sample for your data set, selects the most important features using machine learning. Third, it selects the best methods to visualize the data for a given problem. If your problem is regression, you'll get one set of pictures or charts. If your problem is classification, you'll get a different set of charts. And if your problem is clustering, because you don't have any target variable, it'll do a different kind of pictures, charts. And you can save the charts in PNG, JPG, and JPEG and SVG formats. I'm going to go through this quickly. Why AutoViz? It's systematic, it's simple, and it's explainable. How AutoViz works, there is a lot of design goals. One of them being select the most important features, select the best charts, and deliver them fast. Now, AutoViz was not designed to spend a lot of time generating charts. It is designed to give you a first look at your data within a few seconds. So even for very large data sets, it will take you probably just a few minutes to generate all the charts it needs. So that's the benefit of using underlying NumPy, Pandas, Matplotlib. I don't use any other specialized libraries. Probably use a little bit of Seaborn, but I don't use anything other than the building blocks of Python. So you don't have a lot of I would say external baggage. Implementation, all of this is done. So how do you install AutoViz? Just say pip install AutoViz, and then you import AutoViz class. AutoViz class is the class that holds all your charts. You can run this on your iPad and visualize these charts like the one you're seeing on the right. You can run them on any laptop or any desktop, anywhere. And then you call AutoViz function from AutoViz class. Now the AV class called AutoViz class holds your charts. So if you were to want to save these charts later, it saves them for you in the AutoViz class, and then you can either save them to disk or to files and do whatever you want to do with it. So you call the AutoViz class, give it the name of the file, or you can give it the data frame. So the df is the data frame, the empty string is the file name. Here I'm going to give the data frame because I've already loaded it into a pandas data frame, but sometimes you don't have to load the data frame. You can give the name of the file, the separator that's in the file, and the target variable that you're trying to visualize. Let's say you do not have a target variable, you have a clustering problem. Then you can give your target variable as an empty string, and you will get a different set of charts. So you run, and for running on like 500 rows of data, it takes about 15 seconds on my laptop. So far, how many downloads do we have of AutoViz? We have got about 25,000 downloads of AutoViz. The average is about 500 downloads a week. You can see that the daily downloads are about in the 100 range. And I'm very thankful to everyone who has contributed to it. I also want to mention that if you go to the GitHub called AutoVML AutoViz, and if you click the subscribe button or the follow button, the star, you will be able to bookmark this site. So any changes, upgrades that I make to AutoVML and AutoViz, you'll be immediately notified. So I make changes to AutoVML and AutoViz almost on a weekly basis. So these are constantly being improved. So if you see a feature missing, you're going to miss out if you don't click the star or the follow button on the GitHub. So just remember that. So let's look at a data set, the housing data set. As soon as you click for the Boston housing example, you can see multiple charts. You're going to first see the scatter plot of all of the continuous variables against the target variable. You can see that the number of rooms and the median value, the value of housing goes up as the number of rooms goes up in the house. Similarly, the value of housing falls as the age of the house increases. There are some homes in the Boston housing data set that are nearly 100 years old. So you can see that the median value of housing falls as it goes from a house that's in the 10-year-old, 5-year range to being in the 100-year range. It starts to drop. So you can see the performance of the target variable as the independent variable changes. And similarly, you're going to see each independent variable plotted against another independent variable. So these two variables are somewhat not linearly correlated, but they are somewhat polynomially correlated. So distance and Knox are polynomial correlation, and you can see PT ratio and Knox have somewhat of a similar nonlinear correlation. How are the distributions? These are right skewed, and these are also right skewed. This one is left skewed. So you can see that this kind of skewed distributions are shown to you immediately. So you can decide whether we should transform them or not. These two charts require these two variables, crime and zone, are highly skewed. This one is right skewed very highly. So you may want to do a log transformation. These two variables are not that skewed, so you don't have to do any transformation. So you can make these kind of determinations very quickly. Similarly, when you look at the heat map of all the continuous variables, you'll be able to see which variables are highly correlated to each other. So this particular variable, 0.74, is highly correlated to the target variable, LSTAT. So LSTAT might be an interesting variable for you to include in your model. So you will get ideas on how each variable interacts with not just each other, but with the target variable. So you can decide whether to include them or not in your model. So how to build a better model? The first is you build a model step by step, just as your data scientist would. You remove the low information features. You add some polynomial and interaction variables. You select the model from simple to complex. You add some binning, stacking to your model. If you have some imbalanced data in your data set, you add SMOT, kind of oversampling or other. If you want to do some ensembling, you do some ensembling. Finally, we've now added feature tools to the feature engineering library. So if you wanted to do feature engineering to unlock some additional interactions or additional predictive power in your features, you can now use the feature tools library, and you just have to import feature engineering, which is a module within AutoVML. Finally, when you do all of this, you will have multiple variables that are correlated to each other. So you should select only the best features from the model. So we let you automatically select the best features from the model, and AutoVML will always build you the best model with the fewest number of features. So why AutoVML? Systematic, automatic feature selection. So most of the times AutoVML produces models that are 10% to 99% less number of features. So I was once given a data set with 5,000 variables, and I built a model by using AutoVML. It reduced the number of variables from 5,000 to 50. And that model was able to outperform a model with 5,000 variables. So what does that mean? It means that you can build a model with 99% less number of features in some cases, not in every case. You can build multiple models, test them, you get insights into your data set, and you can now do feature engineering. So how do we do this? We have feature tools, interaction, boosting, bagging, ensembling, imbalanced versus balanced, grid search versus random. You now have feature importances using SHAP. I've also added feature tools library. These three, I need to remove them from the screen, but they're there. So when you go to this GitHub for AutoVML, again, you can click this, and you should be able to see the GitHub there, and you can click start and start it or bookmark it, following it. So first you pip install AutoVML. Next you import AutoVML and call the AutoVML function or method, and then you basically give your train and target and test data. So you don't need to even provide a test data set. If you just had train and target, that's good enough. All other variables are already having defaults. So you don't have to even use more than just two variables, train and target, and the rest of it, it'll do the work by itself. So how many downloads do we have so far? We have about 147,000 downloads and counting for AutoVML as of today. It's currently running. Sometimes it runs in the 3,000 range a week. Sometimes it's currently running in the 2,000 range a week. So it depends on whether there's some talk like today that it's going on. You'll see a spike and then it'll fall down. So it's pretty good adoption. Now we're going to start with the Boston housing data set. We're going to, as you know, it's got 13 variables, 13 predictors. But the first time you run AutoVML, immediately with the linear model itself, you get a feature reduction. It goes from 13 to 10. So you get about a 24% reduction in features, and the time taken is to build a model is 6 seconds. So it selects 10 variables out of 14. And you can see the feature importances. I'm going to show you the root mean square. It's about 3.00. and the normalized RMSE is about 74%. Let's try and move it to random forest. You can see the random forest model produces a slightly better fit. It also reduces the RMSE to 2.525, and the time taken is slightly longer, about 30 seconds. Then you transition to an XGBoost model. It produces, what appears to be a similar kind of a fit, and its RMSE is slightly higher, so it's not going to improve the model that much by moving to an XGBoost model. And if you think that's all to the AutoVML, you're wrong. There's a lot more. So let's try some more. We have more things that we can like tune. First, we are going to take the linear model and add some interaction variables. As soon as you add some interaction variables, you notice that the root mean square error jumps up. It means that the model is getting worse. So we then remove that, and we take the random forest model, which is doing very well, and we now bin the top numeric variables. You can see that the root mean square error immediately drops, and the model has a better fit. Then you try to improve the model by doing ensembling. Well, that makes the model actually slightly worse. The root mean square jumps up again. Finally, you try the XGBoost model and say, I'm going to stack it with a linear model and see if the stacking improves results. And in fact, the stacking does improve the XGBoost model. It's actually going to reduce the errors. So you can do multiple things by sitting just one line of code and changing so many flags. Try this, try that, and you can build the best model. I'm going to give an example with the Wisconsin breast cancer data set. It took 1 minute to train the model, and the accuracy on a linear model itself was 100% on the validation data set. Now, if you thought this was like an overfit or an overfit model, you can compare that to a Keras model that somebody built. I've given the link here, and that Keras model was run multiple times, and it produced, poorer results compared to this. So I'm not saying that this is going to be always better, but it's just one way that you can build a simpler model that outperforms the most complex neural network model, because we focus on the basics. That is, find the fewest number of variables and build your model with the fewest number of features. For example, the Keras model used all the features in the data set, whereas the AutoVML model used, out of the 32 variables, it used only 16 variables. So it reduced the number of variables by 52%. And it took 12 seconds to run, whereas the neural network model took somewhat longer to run. It also got ROC AUC, as you see here, of 100%, while the other model got to about 99 or 98%. Why is the a linear model with fewer features able to outperform a neural network Keras model with multiple layers and so on? Because simple models tend to generalize better than more complex models, and having the fewest number of features helps you explain the model to your audience better than having all of the variables and making the model very bloated and complex, instead of trying to find the best model with the fewest features. And that's what AutoVML was designed to do. So with that, I come to the end of the presentation. We are now going to go into the demo. So what are the next steps for AutoVML? I said earlier that there was feature engineering, but when I created this deck about a year ago, I didn't have feature engineering. So now you have feature engineering. So I should modify this slide. No image or video support. Currently it has NLP, but it doesn't have image or video support. I'm planning to add images so that in one data set, if you had both structured data, text, and image, you can feed that to AutoVML and it'll take care of it. No time series. I've already released a library called Auto Time Series, or AutoTS. You can take a look at it in the same GitHub. And so now we've got time series, finish that. No neural networks. I don't plan to add neural networks or deep learning because I feel like there are a number of tools that already do neural networks. For example, Ludwig from I forgot the company, but you can try to use Ludwig. And model serving, Adding a module for transforming the test data is needed. I haven't built that yet, and once I build it, I'll make it available, which will make it very simple for you to transform the test data the same way as the trained data. Right now, you have to do it manually. AutoViz, what's missing? It's not built into other tools. It'll be nice if others can build this AutoViz into their tools, so you can use it from any number of products. For example, there are a couple of tools already that use AutoViz. It's called Data Assist, and another tool called Ethos. They both use AutoViz for visualization. So if you have a library and that library requires visualization, you can just call AutoViz from there, from your library, and I think a lot of your users will find it very beneficial to view their data. It'll be nice to build AutoViz into educational tools so that students in colleges can use where they have small data sets and students don't have time or the knowledge to write code to visualize data. It'll be nice to build this into an educational software so you can automatically visualize data. And it'll be nice if somebody could add pie charts and mosaic charts and submit them as additional modules to AutoViz, and I can incorporate them and offer additional support. It'll be nice to build this into IoT tools. So automatically IoT tools generate a large volume of data. You don't know what data you're going to get. It'll be nice to incorporate AutoViz into IoT libraries. So thank you. I wanted to take half an hour to the first part of the presentation. So we are done. Now we go to the second part of the presentation for the demo. Any questions? While I pull up the next screen. Okay. We are now going to the next one. Where's this presentation? Okay, StreamYard. Share screen. AutoML Kaggle demo. So now we are going to look at a Kaggle notebook. You can find this Kaggle notebook by searching for AutoVML on Kaggle, and you should be able to see a quick start. You should see all different kinds of notebooks. And this notebook gives you, right, it gives you the ability to run AutoVML on the Titanic data set. So we are going to run. So how is AutoVML different from other libraries? AutoVML is different in being one of the few libraries that I can think of that does automatic feature reduction. All other libraries, I think they take the entire feature set or the data set that you send, and they use all of the features to build a model, which I think is that's what they are trained to do. But I believe that in my job as a data scientist, I found that reducing features was a critical component of building highly successful models that are outperforming with other tools. So if you were to take an example and you compare that to other libraries, you will find that AutoVML uses fewer features, sometimes 20%, sometimes 50% lesser features than the other model, and it produces almost the same results, if not better results, than the other tools. So I would appreciate if somebody uses AutoVML and writes up an article on Medium comparing it to Teapot on some of their data sets, because that'll be a very popular article for many folks, because I get that question a lot. I personally don't want to write an article comparing AutoVML with Teapot because it would be self-serving. If you take any data set, you can pretty much guarantee that your model will run well on certain data sets, and your other tools will run well on other data sets. So you can pretty much skew the results to any way you want, and will not be a fair comparison. So I think it'll be best if somebody else who's a third party is interested in comparing AutoML with Teapot or PyCaret. It'll be a great idea to popularize yourself and also get more readership, because people are interested in knowing how these tools are different. Okay, so let's go ahead, and I'm going to sign in. So I'm signed in. Here's my notebooks. My notebooks are here. So we're going to do the Titanic kernel. Okay, my notebooks. Okay, so here's my demo notebook. I'm going to run this from scratch so we can actually see it. Running, the session is starting. Okay, so the first line is given by Kaggle. The second line is where you need to take your Kaggle data set. Now, the simplest way you can run, in my opinion, Kaggle, is to write the first line and let's just go add data. And you can basically search for any competition data and try it on AutoVML. For example, if you want to try it on the housing prices, you just have to click add, and it will add the data set to your Kaggle kernel. So now if you click data, you'll see the house prices. I've already done that by adding Titanic, and so you will get that here. But if you wanted to add another data set, it's pretty easy. Now we are going to train and test on the Titanic data set. You'll notice that the Titanic dataset train has 891 rows, and the test dataset has 418 rows. Here's where you pip install AutoVML. So you just click pip, and it'll install in 30 seconds or so. While it does that, let me take another question. How to use a hyperparameter tuning? So it does hyperparameter tuning by itself, and so you can very easily do that. So I'm going to post the notebook, and if you don't mind, I'll ask the moderator to cut and paste the link to the notebook for everyone. Okay, so can you please add that to the live comments, sir? Moderator.
Yes, sir.
Okay, thank you. Cut and paste it. So now you can see that there are some errors. That's not unusual in Kaggle's kernel, but they won't. They will not impact you. It is successfully installed, so you don't have to worry. So if you see the word error, I don't want you to panic. It is very normal. All right. So now you then click AutoVML. From AutoVML, install the import the libraries called AutoVML. And the latest version is 0.1.657. This will be changing, so you can anytime see this number constantly moving up. And we're going to give the target. We are first going to build a logistic regression model. And to do the logistic regression model, I'd like you to copy this line and just paste it. So we are going to copy, and then we are going to come and paste it, and that's all you need to do, right? You don't have to remember any commands. You just have to copy paste. Okay, so here we are going to do copy paste, and all we have to do is to take the defaults And here we are going to change the boosting flag, and we are going to change that to none. Why do we do none? Because there are 3 or 4 levels of boosting. When you say boosting flag is none, it uses a linear model. When you change it to false, it uses a random forest. If you say true boosting, then you'll get a XG boost. And if you use the word cat boost, it will create a cat boost model. And you can have any spelling of cat boost. You can have it this way, or you can say cat. Uh, it's any spelling is allowed of cat boost. So I don't want you to think that it's only one kind of spelling. I checked that. So all we have to do is to hit enter, shift enter, and the AutoML starts running immediately. As you can see, it gives you a ton of output telling you what it's doing. So let's look at that first. Okay, so AutoML first tells you it's classifying variables that it found in the data, and you can see that it is having two numeric. This data set has 2 numeric variables, 3 integer variables, 1 string variable, 1 Boolean variable, and 1 ID column. How did it know it was an ID column? So if you go back and look at your data set here, which is your Kaggle, your trained data set. So it already finished, completed the entire modeling while we were even starting to do the display of the data. But take a look at this. You've got passenger ID 1, 2, 3, 4, 5, and you've got survived, which is the target. You've got the class. You've got the name. You didn't have to do anything to to clean the data or to modify any of those variables. It automatically did that for you. And how did it know passenger ID was an ID variable? Very simple. If the length of the number of unique values is the same, then you will use this model. Sorry, the number of unique values is the same as the length of the data set. Then it considers that to be an ID variable. All right, let's go ahead and look at how the logistic regression model did. In terms of imputing missing values, I do not use mean, median, or mode. Why? Because it adds bias to the data set, is what I believe. So I fill the missing values with the word missing, and I use that as a special feature. In addition, I use an extra flag called a missing flag column for each one of the values that has a missing value, and that missing flag column is also added. And so age has some missing values, cabin has some missing values, and embark has some missing values. It adds all of them as missing value flags, and that way you get 3 extra columns. It removes highly correlated features, but currently there are no highly correlated features in this. Now, the number of predictors it found is 13. It's going to reduce those features. It's already reduced them to 12. So one feature was not found not very usable or not very useful to the model. And if you see, the model does pretty well with a logistic regression. You are able to get 80.5 regular accuracy, balanced accuracy, 77%. Got it? And it also gives you a leaderboard with other models. And the best performing model in the leaderboard there is AdaBoost. So if you're going to try other models, you can do that. It gives you all of the charts that you need to make a determination whether this model is any good. You can see the ROC AUC curve. ROC curve shows pretty good AUC 84. You got the PR AUC curve, so you can see that the logistic regression average position is about 80%. You can see the classification matrix. You can see the precision recall FN score and the support. You can see how the model was trained using the parameter C for logistic regression, the penalty for L1 penalty or L2 penalty, the solver that it used currently live linear. So you can see pretty much a lot of information that would help you find, and it also shows you what are the best features. Now, where is the best features here? I thought we saw that. I thought we saw the best features a minute ago. Feature importances. I don't see it here. Okay, so for some reason, a minute ago we saw the best feature importances, but we don't see it now. You can improve the increase the amount of verbosity to 2, and you'll get a slightly more verbose output. So if you want to do that, that's another way to do it. And if you want to do grid search versus hyperparameter search, you can change the hyperparameter tuning to grid search. And we are now going to see whether this model is any better with grid search. So here's the output. So the model has slightly improved with grid search. The RSC is 84, is about the same. Average position is 80, is about the same. All of this is the same. So you can see here the best features. You can also see the SHAP values and so on. So Kaggle does not do some great display, but yeah, now you can see it well. So all of this can be done. You can then submit the target if you are interested in a Kaggle submission. You can immediately submit, right, the values, and you can save the file. Give it a name. Now we're going to do something interesting. We're going to add NLP to the name column. So from AutoML, we are going to import NLP. And we are going to do NLP on the name column. The name column, as you remember, we originally dropped it from using it because the name was not something that AutoML uses. But if you wanted to use name column, all you have to do is to import AutoNLP. And then you can run AutoNLP on the data set, same data set. You will now get a train NLP and a test NLP data frame back. And AutoNLP completes in about 10 seconds. And now you can take the train NLP, which is the new data frame of train with NLP columns added, and you are now seeing 125 columns for this. And it's got sentiment, it's got positive, it's got the number of hashtags, the characters, words in the name. It may or may not improve the model. We're going to find out. Now you're going to run the model with train NLP and test NLP. So the same logistic regression model you're going to run with now 100 and some features. It's already reduced the 117 features down to 54. That's about a 50% reduction in features automatically. So you got the result, and it's slightly better. It's about 80%, 81% balanced accuracy. You can see that the ADA boost is still doing well. Here are the top features. The top features now are more NLP features. 6 has now moved down in terms of feature importance in parts. I do not recommend that you do NLP on name, but it is just an example of how to use NLP that's embedded in AutoML in order for you to improve your models. All right. And finally, if you wanted to run AutoML with XGBoost, we're going to just run AutoML with XGBoost. So all you have to do is to change the boosting flag to true, and now you'll get an XGBoost model. And that takes about a minute to run. So the XGBoost model is about the same, 80% as the linear model. It's 85% AUC, so slightly better, about 81% average position. Though it looks like it can benefit a little bit from running more maybe epochs or more estimators. And you can see here the results. The XGBoost did a pretty nice job. Sex is now the leading feature importance. Cabin missing, whether the cabin is flag is missing, cabin variable is an important indicator. The passengers class is an important indicator of whether they'll survive or not. So I'm going to stop here on AutoVML, and I'm now going to switch to AutoViz. Any questions? While I look for a different example. Okay, AutoVML. Okay, so I've already explained how it's different from other AutoML libraries, so I hope that was helpful. I'm now going to go into AutoViz and demo that. So the AutoViz demo, as you're seeing here, is quite simple. You should just use the first line to get your input data. This is where you install AutoViz. So you click, you type pip install AutoViz. So it'll automatically install. Once it is installed, call the AutoViz class. And the AutoViz class will tell you what to do. So all you have to do is to AV AutoViz class. And then you have an option to do multiple, right? We're going to, same example, but I'm going to take the Boston housing data set. So in this case, the Boston housing data set is a regression data set. And we are going to run the target variable median value. And we're going to look at how AutoViz runs on this data set. So how did we get this av.autoviz? That you get from importing AutoViz. As soon as you import, it gives you the calling function. So the calling function is just this av.autoviz, and all you have to do is to copy this, and you have to come here and paste it. So I hope everybody can see that. And while we were doing that, it already finished running. So it took 5 seconds or 6 seconds to run on the data set. So we're going to see how well it did. So you can see in the charts here that AutoViz draws first each variable against the target variable. So index against median value, crime against median value. You can see that, as we showed earlier, room, as a number of rooms increases, your median value of housing increases. And we saw earlier that as the LSTAT increased, your housing kind of values plunged. So I'm now going to share the notebook for AutoViz as well, the demo notebook. Sorry, it's right here. All right, so you can see that if you do a continue the pairwise scatter chart. So moderator, if you can copy paste the AutoViz Kaggle notebook to the live comments. Thank you.
Yes, sir.
Yeah, can you share the notebook link from the Kaggle? I posted on private chat.
Okay, sir.
Thank you. Copy pasted. So you can see here that each variable is plotted against the other variables in the data set. This may take a little while if you have hundreds of variables, but you can limit the number of variables you are seeing in your data set. The maximum rows analyzed input variable and the maximum columns analyzed. So the maximum number of columns I've limited to 300, the maximum rows to 150,000. You can change that to any number that you want. So yeah, I'll come to that question. Let me finish AutoViz. There is a lot of charts that AutoViz produces, like we can see here. Every variable that's numeric is plotted here, and even the categorical variables are plotted. This is you know, a data set, so it's got kind of multi heads. distribution. It's not very normal. And you can see the distribution of the categorical variable. I said that these two variables, zone and B, needs to be kind of transformed. You can leave the rest here. You can also see the heat map of all the variables in the heat map. The ones that are in lighter color are the highest correlation. So if you look at the heat map and the dark ones, the highest negatively correlated, these minus 0.74, minus 0.61 variables are highly correlated to each other. So you might want to consider removing them if two variables in this and this, for example, are highly correlated, Knox and this are highly correlated. You may need to reduce some variables there. So think about that when you're building a model. AutoML does that automatically. You don't have to worry about it. But in AutoViz, you are able to see very clearly which charts are useful and which charts are not very useful, which variables. You can look at the average crime by radial distance. You can see the average index by radial distance. There are very large number of charts that you're going to see for just even a small data set. Now I'm going to change and move to the second, which is the Titanic data set. So we're going to change it to Titanic. Reduce train. Reduce. It's not called train one. It's just called train. We're going to change the target to survived. And then we're going to change the data here to reduce train. Now it's going to run on the Titanic data set. And you can see that the charts change immediately to a different look and feel, depending on what problem is being analyzed. So here you're seeing that the chances of survival vary with age. And those who have survived tend to be younger in this cluster here, and a little bit older. And similarly, you can see that the fare, those who paid a high fare had a higher chance of survival. And if you look at the age, the scatter plot for age against fare, you can see that there is not much of a correlation between age and fare, except that higher, older people paid somewhat of a lower fare compared to younger people. And the distribution of the passenger class variable, the distribution of gender, male, female, among the males, you can see that many of them did not survive, whereas among the females, many of them survived. A bigger black box means that many of them survived. So black here means many of them did not survive because it's a small box. This is a big box. So those are things that will help you follow this data set. And it's all very simple with just one line of code. I'm going to stop here and take questions because we are end of the presentation. So I'm going to take this question. How do we make it run on multi-class text data distribution? So it's two things. AutoML automatically will turn a large text variable, but if it does not detect it as a variable, text variable, you may want to transform it because the name variable, like I showed you in the Titanic data set, was not automatically detected. The reason was the variable itself did not look like a text variable. A text variable is something that's got at least 50 characters in it, and it's one of those criteria that AutoML looks for. Any other questions?
As of now, no more questions, I guess. So I hope you would spare some time later so that you could address these questions from the comment section later on.
Sure.
So, and I would like to thank you for being with us here today and conducting such an informative session. So thank you, sir.
Thank you. Thank you very much for the opportunity. Really enjoyed it. Thanks, sir.
And to the audience, I would like to thank you all for watching this video. And I hope you guys are doing well during these times. And as I've said before, we conduct events like this every week. And if you want to stay updated with these events, you could check out the links in the description. And keep learning, stay home, stay safe. Goodbye.